Ever felt that surprising pushback when you try to run in water or, just the force of the wind hitting you on a really gusty day?
Yeah, absolutely.
These aren't just like small annoyances.
Yeah.
They're everyday examples of these, well, powerful invisible forces all around us. Today, we're doing a deep dive into external flow, drag and lift. Our mission: we want to unpack the physics behind these forces. We'll look at how they shape pretty much everything, from the cars we drive, the planes flying overhead, even how a baseball curves. We're pulling this from a detailed engineering textbook, sort of giving you a shortcut to understanding these really core ideas.
And it's funny, these forces might seem simple on the surface, like it's just air pushing on stuff, right?
Right.
But there's actually a surprising amount of depth, some really counterintuitive things going on, complex interactions. It's more fascinating than you might think at first.
All right, let's get into it. This fundamental idea. External flow. What is that exactly?
Well, basically, it's just about how a fluid could be air, could be water, moves over an object that's sitting inside it.
Okay, like wind around a building.
Exactly. Or, say, a submarine moving through the ocean. And here's a key point. The fluid's stickiness, its viscosity,
Yeah.
it's not the same everywhere. It's mainly concentrated in this thin layer right near the surface, the boundary layer.
Oh, okay.
And then also in the messy, disturbed flow behind the object, we call that the wake. Outside of those zones, the fluid acts almost like there's no friction.
So when the fluid and the object interact,
Mm-hmm.
what forces actually pop up?
Right, two main ones. First, there's drag force. That's the resistance, the component acting in the direction the fluid is flowing. It's that pushback.
When you feel.
Exactly. And then there's lift force. That's the component acting perpendicular or normal to the flow direction. That's what makes things go up, basically.
And these aren't completely separate things generating them.
No, that's important. Both drag and lift come from a combination of two things: pressure, pushing perpendicular to the surface, and friction, or shear forces, acting parallel to the surface. Both contribute to both.
Okay, let's make this concrete. Examples. Drag is.
Drag is the force on your car as you drive. The force-making power lines sway in the wind, even on trees, underwater pipelines.
Lots of things. And lift.
Lift is what bird wings generate, obviously airplane wings too. But it's also why tiny things like raindrops or snow or even dust particles can get carried upwards in a gust of wind.
And engineers have to grapple with this constantly, right?
Oh, absolutely. Understanding drag and lift is, well, fundamental. Designing aircraft, cars, even buildings, ships, submarines, wind turbines, it all depends on this. Just look at modern cars. That focus on aerodynamics. It's directly cut fuel consumption, made them quieter, improved handling. It's huge.
Interesting. You also mentioned something about relative motion.
Yes. This often trips people up initially. It doesn't matter if the fluid is moving over a stationary object, like wind over that building,
Okay.
or if the object is moving through still fluid, like a car driving through calm air.
It's the difference in speed that counts.
Exactly. Only the relative motion matters. And that's super useful for engineers. It's why we use wind tunnels. We can just blow air over a stationary model of, say, an airplane wing, instead of having to fly the real thing for every single test. It simplifies things enormously.
Makes sense. So how do we start classifying all these different flow situations? It seems complex.
It can be. We often break it down first by dimensions. Is the flow basically two-dimensional, like over a very long pipe or cable stretched perpendicular to the wind?
Okay.
Or is it axisymmetric, meaning it has rotational symmetry like a bullet moving through air?
Right.
And then, of course, there's full three-dimensional flow, which is what you get with something complex like a car.
And what about the fluid itself? Does it compress?
Good question. That's compressibility. At lower speeds, like for cars or submarines, the fluid density doesn't really change much, so we call that incompressible flow.
But for a jet?
For high-speed aircraft, jets pushing towards the sound barrier, the air definitely compresses. That's compressible flow, and the physics gets a bit more complicated.
And the shape of the object itself must matter hugely.
Absolutely. We broadly talk about streamlined bodies versus bluff bodies, sometimes called blunt bodies.
Streamlined is like sleek.
Yeah, think race cars, airplane wings. They're shaped to align with the flow, minimize disturbance, they look contoured.
And bluff.
Bluff bodies are the opposite. They kind of block the flow. Think of a brick or a big truck or even just a flat plate facing the wind.
And streamlined is generally better for moving through fluid.
Generally, yes. Much less resistance.
Okay, so we have these forces, different flows, different shapes.
Yeah.
How do we actually measure and compare them? Like, Apple to apples.
That's where dimensionless numbers are key. We use the drag coefficient, or CD, and the lift coefficient, CL.
Coefficients, like a rating.
Sort of. They take the actual measured force, drag force, FD, or lift force,
Yeah.
FL, and they normalize it. They divide it by the dynamic pressure.
Dynamic pressure, that's the term with velocity squared.
Exactly. 1/2 times the fluid density times the velocity V squared, and also divide by a reference area A.
What's there?
Depends on the body. For bluff bodies like cars, we typically use the frontal area, the area you see looking straight at it. For thin things like wings, we use the planform area, the area you see from above.
So these coefficients let you compare a model car in a wind tunnel to a real car on the road.
Precisely. Let's use that textbook example. A car going 60 miles per hour, standard air conditions. Its frontal area is about 2 square meters.
Okay.
If you measure the drag force in a test and it comes out to, say, 302.5 newtons,
Yep.
you plug those numbers into the formula and you find the drag coefficient, the CD, is 0.34.
And that 0.34 value is useful for comparing it to other cars tested the same way.
Absolutely critical for comparing designs. Standardization is key.
Got it. And just quickly, before we really dig into drag, you mentioned terminal velocity.
Yes. That's a great example of these forces balancing out. When something falls, like a skydiver or even a raindrop,
Yeah.
it accelerates due to gravity, but the drag force pushing up increases with speed. Eventually, the drag force plus buoyancy exactly balances the weight.
So it stops accelerating.
Right. It reaches a constant maximum speed, its terminal velocity. It just coasts down after that.
Okay. Interesting balance. Now, let's really unpack drag. You said it's not just one thing.
Correct. It's fundamentally made up of 2 parts. First, there's skin friction drag. This comes directly from the sheer stress, the friction between the fluid and the object's surface.
Like rubbing.
Kind of, yeah. It depends a lot on the fluid's viscosity and the total surface area that's parallel to the flow. If you have a flat plate perpendicular to the flow, friction drag is 0. Parallel, it's maximum.
And the second part.
That's pressure drag, sometimes called form drag. This comes from pressure differences around the body. Higher pressure pushing on the front, lower pressure pulling from the back.
And shape matters more here.
Hugely. Pressure drag is dominant for bluff bodies. For those thin, flat plates parallel to the flow, it's negligible. It gets really significant when the flow separates from the body.
Okay, this separation sounds important, but first, streamlining. How does that play with these 2 types of drag? It seems like it should just reduce drag overall.
Well, yes and no. Here's the interesting trade-off, the sort of paradox. Streamlining works by delaying that flow separation we just mentioned. This drastically reduces the pressure drag component.
Good.
But to make something streamlined, you usually need to stretch it out, make it longer and sleeker, which increases the surface area.
So more surface means more friction drag.
Exactly. So streamlining decreases pressure drag, but increases friction drag. The goal in design is always to minimize the total drag, the sum of the 2.
So there's a sweet spot.
Precisely. The textbook shows there's often an optimal thickness or shape that gives the minimum total drag. And things like fairings, those smooth covers you put over, say, landing gear struts,
Yeah.
they can cut the drag of a blunt component down massively, maybe to just 1/5. It's all about managing that trade-off.
You keep mentioning flow separation. Let's focus on that. What exactly is happening?
Imagine fluid flowing smoothly over a curved surface. If the curve is too sharp or the velocity too high, the fluid can't stick to the surface anymore. It detaches.
Like a car skidding on a turn.
That's a decent analogy, yeah.
Mm-hmm.
The fluid stream literally separates from the body's surface.
And what happens then?
Behind the separation point, you get this region of swirling, low-pressure fluid called the separated region. And trailing behind that is a whole area of disturbed lower velocity flow.
And why is that bad for drag?
Because that low-pressure separated region behind the object effectively pulls it backward, creating a large pressure difference between the front and back. A bigger separated region means much bigger pressure drag. Controlling separation is key.
And this has real consequences, right? Like for airplanes.
Absolutely critical. Think about airplane wings. If they tilt up too much relative to the oncoming air that's a high angle of attack, the flow can separate over the top surface.
And that causes
a drastic loss of lift. The plane stalls. It's incredibly dangerous and has unfortunately been a factor in many accidents.
Oh.
Even seemingly small things, like ice or snow building up on a wing, can change its shape just enough to cause early separation and loss of lift.
And there's something called vortex shedding, too.
Yes, that's another effect related to the wake. Behind bluff bodies especially, you can get these swirling structures, vortices, peeling off alternately from the top and bottom.
Like little whirlpools.
Kind of. And if the frequency they shed at matches a natural frequency of the structure, say a bridge or even a wing, it can cause dangerous vibrations, resonance. The Tacoma Narrows Bridge is the famous cautionary tale there.
So shape and orientation are just crucial.
Enormously. Take a simple hemisphere. If the round side faces the flow, the CD is about 0.4.
Okay.
Flip it, so the flat side faces the flow. The CD jumps to 1.2, 3 times the drag just by turning it around.
That's a huge difference.
Or just rounding the corners on a square rod can cut its drag almost in half, maybe from 2.2 down to 1.2. Small shape changes, big effects.
And we see this drive for low drag not just in machines, but in nature, too.
Oh, definitely. Dolphins are incredibly streamlined. Their CD is remarkably low, like 0.0035, almost like a perfect flat plate.
Yeah.
Birds tuck their feet, extend their beaks. Airplanes retract landing gear, same principle. Even plants adapt. Leaves curl up, branches cluster, trunks bend in high winds, all to reduce drag.
And athletes.
Absolutely. Look at Olympic cyclists and their teardrop helmets. Skiers in their tuck positions, swimmers shaving their bodies. It's all about minimizing that drag force by even tiny amounts because it makes a difference.
Let's bring it back to vehicles.
Yeah.
You mentioned car CDs have dropped a lot.
Yeah, huge improvements. We see a range now from maybe 1.0 for a big, boxy semi-trailer
My drag.
down to maybe 0.4 for minivans, and the best passenger cars are around 0.3 or even a bit lower now. Generally, the blunter it looks, the higher the CD.
And those fairings on trucks really work.
They do. They can cut a semi's drag by maybe 20%. And a good rule of thumb for highway driving is that your percentage fuel saving is roughly half the percentage drag reduction.
So a 20% drag reduction saves about 10% fuel.
Roughly, yeah, at highway speeds. Which is why car companies went from CDs of like 0.8 back in the 1920s down to 0.3 today. It's a massive fuel saving.
And what about drafting, like cyclists?
Drafting is huge. A cyclist riding right behind another can cut their drag coefficient almost in half, from maybe 0.9 down to 0.5. It makes an enormous difference.
And just how we drive matters too, right? Speeding.
Definitely. Drag goes up with the square of velocity, so doubling your speed means 4 times the drag. Speeding just eats fuel.
Windows open, arm hanging out.
Yep, increases drag. Actually, for some very aerodynamic cars, running the AC at highway speed might be more fuel efficient than opening the windows because the drag penalty from the open windows is so high.
That's surprising. You had a great example about car height, too.
Yeah, the textbook calculation.
That's
If you
right.
just reduce a car's height slightly, say from 1.7 meters to 1.55 meters, keeping the width the same.
That's like an 8 or 9% reduction in frontal area.
Right. For a typical driving distance, like 18,000 kilometers a year at highway speed, that small design change could save you around 64 liters of fuel a year. Maybe $60 or so, depending on fuel prices.
That's real money, just from a slightly sleeker shape.
It absolutely adds up. Every little bit of drag reduction counts.
Now, you mentioned sometimes engineers add up drag from simple parts to estimate the total.
Yes, the idea of superposition. For really complex shapes, you might try to approximate the total drag by adding up the drag of its simpler components.
Does that work well?
It's okay as a first guess.
Okay.
But it has limits. The way the flow interacts between different parts means you can't just add them up perfectly. It ignores the interference effects. So useful sometimes, but needs caution.
Okay. We've taught complex shapes, bluff bodies.
Mm.
What about the simplest case? Just flow going along a flat surface? Parallel flow over flat plates.
Right, seems basic, but it's fundamental. The key concept there is the velocity boundary layer.
That sticky layer again?
Exactly. It's the thin region near the plate where the fluid speed goes from 0, right at the surface, that's the no-slow condition. Fluid sticks to the wall up to the full speed of the flow further away, the free stream velocity.
And for a flat plate parallel to the flow, is it mostly friction or pressure drag?
For a smooth, flat plate perfectly aligned with the flow, the pressure drag is basically 0. So the total drag is pretty much all skin friction drag.
How do we measure that friction?
With the friction coefficient, CF, there are formulas for it, depending on whether the flow in the boundary layer is smooth and layered, that's laminar flow, or chaotic and mixed turbulent flow.
Does roughness matter?
Hugely, but only in turbulent flow. If the boundary layer is turbulent, surface roughness significantly increases friction drag. If it's laminar, roughness typically has almost no effect, as long as it's small enough to stay within that smooth layer.
Can you give an example of calculating this?
Sure. A book has one. Engine oil at 40 degrees C, flowing over a 5-meter-long flat plate at 2 meters per second. You calculate the Reynolds number first to see if it's laminar or turbulent. In this case, it's about 40,000, which is well within the laminar range for a flat plate.
So smooth flow.
Right. Then you use the laminar friction coefficient formula, and you find the drag force per unit width of the plate is about 58 newtons.
58 newtons. What's that like?
It's roughly the weight of a 6-kilogram mass. So even just oil flowing smoothly over a plate generates a noticeable force.
Okay. Now, cylinders and spheres, you said they're more complex.
Oh, much more complex than flat plates. The flow patterns around them are intricate. You get a stagnation point at the front, the boundary layer develops, then it separates, and you get this big, messy wake behind them.
And the drag changes with speed.
Dramatically. At very low speeds, low Reynolds numbers, maybe below 10, the drag is mostly friction. But as speed increases, Reynolds number above, say, 5,000, pressure drag completely takes over because of that flow separation and wake.
And there's something really weird that happens. The drag crisis.
Yes. This is one of the most fascinating, counterintuitive things in fluid dynamics. For cylinders and spheres, as you increase the speed, the drag coefficient actually drops suddenly and dramatically around a Reynolds number of 200,000 or so.
It drops. Drag gets lower at higher speeds.
The coefficient drops. What happens is the boundary layer itself transitions from laminar to turbulent before it separates.
Okay. Why does that help?
Because a turbulent boundary layer has more energy, it can resist separating longer, it stays attached to the surface further around the back of the sphere or cylinder.
Ah, so the wake gets smaller.
Exactly. A smaller wake means less pressure difference between front and back, which means less pressure drag. So even though turbulent flow might slightly increase friction drag, the reduction in pressure drag is so massive that the total drag coefficient plummets.
That is weird. Because for streamlined bodies, turbulence usually means more drag.
Right. It's the complete opposite effect for these bluff bodies. Very counterintuitive.
So how does this apply in the real world? Can we use this effect?
Absolutely. Think about surface roughness. We said roughness increases friction drag in turbulent flow.
Yeah.
But for a sphere or cylinder near that critical Reynolds number, adding roughness can actually trip the boundary layer into becoming turbulent earlier at a lower speed.
And that causes the drag crisis to happen sooner.
Precisely. Which means you get that big drop in drag coefficient at speeds where it would normally still be high.
And a classic example is?
Golf balls. Those dimples aren't just decorative. They're precisely engineered roughness elements.
To make the flow turbulent.
Yes. They trigger turbulence in the boundary layer, delaying separation, shrinking the wake, and drastically reducing pressure drag. A dimpled golf ball can have roughly half the drag coefficient of a smooth one at typical hitting speeds.
Which means it flies much further.
Much further. That's why golf balls have dimples. Table tennis balls, on the other hand, are smooth. Because they travel slower and are smaller, their Reynolds numbers typically never get high enough to reach that drag crisis region where dimples would help. So smooth is better for them. Isn't that cool?
That is really cool. Engineering exploiting a weird physics quirk. Do you have a number for the forces involved, say on a pipe?
Yeah, another example from the source. Imagine a pipe, maybe 2.2 centimeters in diameter, stretched across a 30-meter wide river. The water's flowing at 4 meters per second.
Okay, fast flow.
The Reynolds number is about 77,000. For a smooth cylinder at that re, the drag coefficient CD is about 1.0.
So what's the total force on the pipe?
When you calculate it out, the total drag force from the river pushing on that relatively small pipe is around 5,300 newtons.
5,300 newtons. That sounds like a lot.
It is. It's like hanging over 500 kilograms, more than half a ton, off that pipe. Shows you the immense forces fluids can exert and why structures in water or strong winds need to be engineered so carefully.
Wow. Okay, let's switch gears now. We've talked a lot about drag, the resistance. Let's talk about lift, the force going upwards, perpendicular to flow.
Right. For things like airplane wings or airfoils, lift is almost entirely due to the pressure distribution. Because they are so streamlined, the viscous friction part is usually pretty small, negligible often.
So it's all about pressure differences. How does the shape create that?
The classic airfoil shape is curved on top, flatter on the bottom. This forces the air flowing over the top to travel a slightly longer path, so it speeds up.
And faster air means lower pressure. That's Bernoulli.
Essentially, yes. Faster flow on top means lower pressure on top. Slower flow underneath means higher pressure underneath. That pressure difference, integrated over the whole wing surface, creates a net upward force that's lift.
But you mentioned earlier that simple theories predict zero lift.
Ah, yes, the paradox of potential flow theory. If you ignore viscosity completely, the math says an airfoil shouldn't generate lift, which is obviously wrong. Airplanes do fly.
So what's the missing piece?
It comes down to circulation and how the flow behaves right at the sharp trailing edge. The fluid can't actually make an infinitely sharp turn there. It has to leave the trailing edge smoothly.
Okay.
This smooth departure condition forces a circulation, a kind of swirling motion, to be established around the airfoil. It's this circulation combined with the forward motion that increases the speed over the top and decreases it underneath, creating the pressure difference and thus the lift. It's a subtle but crucial effect tied to viscosity, even though viscosity's direct force contribution is small.
Okay, that makes more sense. So for designing wings, what's the key metric?
A really important one is the lift-to-drag ratio, CLCD. You want as much lift as possible for as little drag penalty as possible. High efficiency means a high CLCD ratio.
And how does tilting the wing, the angle of attack, affect this?
As you increase the angle of attack, lift generally increases pretty much linearly up to a point.
The stall point.
Exactly. Beyond the stall angle, the flow separates drastically over the top surface, lift plummets, and drag shoots up. So you get more lift, but also more drag as you increase the angle of attack until you hit that stall limit.
Which is why planes have flaps.
Precisely. Those movable flaps on the front, leading edge, and back, trailing edge, of the wings are amazing. They temporarily change the wing's shape.
To do what?
To generate much more lift at lower speeds, which is essential for takeoff and landing. They allow the plane to fly safely at speeds that would be too slow for the clean wing configuration.
But there's a trade-off. More drag.
Oh, yes. Deploying flaps significantly increases drag, maybe 5 times the drag compared to no flaps. But that high drag is acceptable for the short periods of takeoff and landing, because the high lift capability is essential.
And sometimes flaps has gaps in them. Slots.
Yes, those slots are clever. They allow high-pressure air from underneath the wing to flow through the slot and energize the boundary layer on the top surface, helping it stay attached longer and preventing separation, which further boosts lift.
So we can actually calculate the minimum speed a plane can fly, the stall speed.
We can estimate the minimum flight velocity, Vmin, yeah. It depends on the maximum lift coefficient the wing can generate, CLmax, the wing area, A, the air density, and the aircraft's weight, W. The formula is basically Vmin equals the square root of 2W CLmax A.
And pilots don't fly right at that speed.
No, definitely not. For safety, regulations like the FAA require operating at a margin above stall speed, typically 1.2 times Vmin.
And air density matters here, like at high altitudes.
Big time. Air is less dense at higher altitudes, like in Denver or on hot days. Lower density means you need a higher speed to generate the same amount of lift.
So you need longer runways.
Exactly. High-altitude airports need longer runways, especially in the summer, to allow planes to reach those higher required takeoff speeds safely.
Let's look at that airplane example again. A 70,000-kilogram plane, 150-meter wing area. What's the speed difference with flaps?
Right. Without flaps, its minimum safe takeoff landing speed, 1.2 times Vmin, is calculated to be about 85.1 meters, which is 306 kilometers. Pretty fast.
Okay, and with flaps?
With double-slotted flaps deployed, maximizing lift, that minimum safe speed drops to 56.2 meters, or only 202 kilometers. A huge reduction makes operations much easier and safer.
That's dramatic. And when it's cruising high up, say 12,000 meters at 558 kilometers.
At that altitude, the air density is very low, about 0.312 kilometers might. To generate enough lift to support its weight, it needs a lift coefficient of 1.22. Looking at airfoil data, that typically corresponds to an angle of attack around 10 degrees.
And the power needed just to overcome the wing's drag.
It's enormous. The calculation shows it's about 2,620 kilowatts. That's over 3,500 horsepower just fighting wing drag at cruise altitude. Shows you why aerodynamic efficiency is paramount in aircraft design.
Now, real wings aren't infinitely long. They have tips. Does that change things?
Yes, significantly. That's the concept of finite span wings and induced drag.
Induced drag? What's that?
Because the pressure is higher on the bottom surface of the wing than the top, air tries to leak around the wingtips from bottom to top. This leakage creates swirling masses of air trailing from the wingtips, called tip vortices. You can sometimes see them on damp days as vapor trails.
And they cause drag.
Yes. These vortices alter the airflow over the wing and effectively tilt the lift vector slightly backward, creating an additional drag component that wouldn't exist on an infinitely long wing. That's induced drag. It's purely a 3D effect.
And these vortices can be dangerous.
They can be very strong and persist for a long time behind large aircraft. This wake turbulence is a serious hazard to smaller planes following behind, which is why air traffic control enforces separation distances, impacting airport capacity.
I've heard birds use this somehow, flying in a V.
Exactly. Geese, ducks, even pelicans flying in that V formation are incredibly smart. Each bird, except the leader, positions itself slightly behind and to the side of the bird in front, flying in the upward moving part of the air generated by the tip vortex, the upwash.
So they get a free lift boost.
Pretty much. It allows them to save a significant amount of energy. Studies suggest maybe up to a third less effort compared to flying alone. Military jets sometimes use the same principle in formation flying. Nature figured it out first.
So the shape of the wing, its span versus its width, matters for this induced drag.
Yes, that's the aspect ratio, AR. The ratio of the wingspan squared to the wing area, or roughly span divided by average chord length. Long, narrow wings, like on gliders or large airliners, have a high aspect ratio.
And that's good for efficiency.
Yes, high AR wings have less induced drag for the same amount of lift, making them more efficient for cruising, but they tend to be less maneuverable.
Whereas fighter jets.
Fighter jets need agility, so they often have short, stubby wings with a low aspect ratio. They pay a penalty in induced drag, but gain maneuverability. It's another design trade-off.
And those little upturned bits at the end of airliner wings? Winglets.
Winglets, or sometimes end plates, are specifically designed to disrupt that flow around the wingtip, weakening the tip vortices and thus reducing induced drag. They improve fuel efficiency, especially on long flights.
Okay, one last effect related to lift, spinning things, the Magnus effect.
Ah, yes, the Magnus effect. This is lift generated simply by the object spinning as it moves through the fluid.
How does spinning create lift?
The rotation drags fluid around with the surface. On one side of the spinning object, relative to the oncoming flow, the surface motion adds to the flow speed. On the other side, it subtracts.
So like the airfoil, you get different speeds on different sides.
Exactly. Different speeds mean different pressures, again via Bernoulli's principle. This pressure difference creates a net force perpendicular to the main flow direction that's lift due to spin.
And this is big in sports.
Huge. Tennis players use topspin to make the ball dip down faster, or backspin, slice, to make it float longer. Golfers use backspin for lift and distance. Baseball pitchers use spin to make pitches curve, slide, or drop dramatically. It's all the Magnus effect in action.
Does it affect drag much?
Generally, the effect of spin on drag is relatively small compared to its effect on lift. The lift coefficient can become quite large depending on the spin rate.
Let's take that tennis ball example. Hitting it with backspin. Does it actually go up?
Not usually against gravity. The example calculation is for a standard tennis ball hit at 45 mph with a pretty fast backspin, 4,800 RPM.
Yeah.
The Magnus effect generates an upward lift force of about 0.036 pounds force, but the ball's weight is 0.125 pounds force.
Well, gravity still wins.
Yes, the net force is still downwards, 0.089 pounds down. The ball will fall. But crucially, it falls less steeply than it would without spin.
Ah, so the backspin makes it travel further before hitting the ground.
Precisely. It stays airborne longer, counteracting gravity partially. That's why backspin helps achieve distance in sports like tennis and golf.
Fascinating. Before we wrap up, it feels like we have to mention the Wright brothers.
Absolutely. Their contribution wasn't just building the first successful airplane, it was how they did it. They were methodical engineers.
How so?
Instead of just building whole planes and crashing them, they broke the problem down. They built wind tunnels, they tested wing shapes, airfoils systematically, they studied propellers separately, they gathered data.
A scientific approach.
Exactly. They applied fundamental principles, collected data, and used it to design. They really laid the groundwork for modern aeronautical engineering and showed how understanding these very concepts of lift and drag and measuring them carefully was the key to controlled flight.
What an incredible journey we've taken. We started with just, feeling the wind or resistance in water.
We got everyday stuff.
And we've unpacked the basic definitions of drag and lift, dug into the details of pressure versus friction drag, the whole idea of streamlining.
That flow separation, which is so critical, leading to stalls.
Right. And then the physics of flight itself, how wings work, how flaps help, even how a spinning ball gets that curve. It's amazing how much is going on.
It really is. And understanding these principles, it's not just for engineers building planes or cars. It gives you, I think, really valuable insights into how the world works all around us.
Yeah, from efficient transport to just watching a bird fly.
Exactly. And it makes you wonder, what's next? There's ongoing research into things like these micro actuator arrays to actively control turbulent boundary layers, reduce drag even further.
Really, trying to actively manage the flow.
Yeah, it raises the question, how will these kinds of advanced techniques continue to reshape, the future of vehicles, of flight efficiency? Where are the next big gains going to come from?
That's a great thought. So hopefully for everyone listening, the next time you see a sleek car
Yep.
or watch a plane take off, or maybe even tee up a golf ball,
Hmm.
you maybe see it a bit differently. Observe the world through this lens of drag and lift. You start noticing it everywhere in all sorts of ingenious ways, both engineered and natural. Maybe you won't look at them quite the same way again.